our discussion panel. Welcome you all.
Hello, everyone. Hi, I'm Jordan Boyle from Leeds in the UK. Nice to meet you all.
Hello, everyone. Thank you very much for being with us. Thanks, Professor Stanislav Gorb. Thank you, Professor Jordan Boyle. So first of all, I would like to say that time is the most valuable thing a person can spend. So on behalf of my colleagues and I, thank you very much for spending this time with us here. Thank you.
Welcome.
It was a big pleasure. Thank you so much.
We've got a few questions from the audience. Clara is going to be helping us for the time of this table, the round table. Is there anyone you would like to say before we start with the questions? Professor Gorb, Professor Jordan?
No, I'm certainly happy to jump into the questions, and I imagine the conversation might, develop organically from there. I saw your presentation, Stanislav, and a very interesting piece of work that will hopefully come.
Thank you so much. You can start if you wish. I just try to get these numerous questions we already have in the question and answers. Actually, it should be called just questions.
Então, para começar, temos uma pergunta da Patricia Howard, que também...
Patricia Howard, there is a question. She will be one of the lecturers, a very interesting questions. And I'd like to say...
But does not mean that it's not as complex as those that invest in more resources in reproduction. For example, vision. How does this relate with swarm robotic development? Does it also require, for example, vision?
Okay, cool, thank you. Yeah, so I saw that question in the text, which is good because the start of you speaking was cut off by the English translation. But yeah, so I mean, you're right that swarm robots could potentially benefit from visual systems. A classic robotic vision system is quite expensive in terms of, financial cost and the sort of size and power of computing element that's required for that. There's been some interesting work done by people, not myself, on like insect-inspired vision, which can do like obstacle detection, feature extraction in a computationally efficient way on dedicated hardware. But I think in swarm robotics, we should certainly consider trying to do without vision. There are lots of animals that use other sensors, chemical and touch sensors primarily, I suppose. So I think in some cases you might not need vision and could, perceive your environment in a different and cheaper way. I hope that was a satisfactory answer. These things, of course, it always is so much more natural when you're all in the same room. Doing a discussion like this online always feels a bit weird.
Oh, sorry, I had to mute my mic. Professor Gorb, one question for you. Professor Gorb, excellent presentation, thank you. I noticed that you mentioned important work done by you, especially in the first decade of the century. Do you currently concentrate your activities on adhesion, or are you directing your research to other properties?
Okay, thank you so much for this question. Of course, adhesion is a topic which follow us at least, I would say, last 20 years, because there are so many different kinds of adhesion. In today's talks, we've spoken mainly about this reversible adhesion, where we can bond and debond and million of cycles and so on. But of course, there are many more interesting adhesive kind of systems in a biology, and of course with a potential for applications. But in general, we are very much interested in different kind of surfaces, because as soon as you understand adhesion, the next question is how plants, for example, prevent adhesion of some specialized insects. And I think this topic is not only interesting for biologists and engineers, but it is also interesting from the point of view of agriculture, because potentially you can breed plants species, not species, but sorts with the corresponding properties which prevent insect attachment and so on. So adhesion is a topic, but also anti-adhesion is automatically a topic, and we have a couple of botanists in the group. They exactly look at these kind of properties. And then the next thing, if you understand surfaces and understand these contact mechanics at biological surface, you can, or what we do, we look at friction kind of questions. For example, there are many publications. If you go to our website, you will realize we also work on snake friction. I'm entomologist by training, but some years ago we started to look on the belly surface of snakes. And I was absolutely convinced that vertebrates, they are so well studied usually, but we realized there was actually almost no paper at that time. People usually look at something colorful on the back, but very seldom on boring white surface on the belly. But from mechanical point of view, it's much more exciting. So we look at different animals and plants with interesting surface properties, with interesting contact mechanics problem. That's where we are.
Do you mind if I jump the queue with a question for Stanislav? So do you think it would be possible at this point to make an artificial material with the asymmetric friction properties that we see on snake bellies? Because
yes, absolutely.
Snake robots, that would obviously be very helpful.
Absolutely, we're working on that, and we work with people from the robotic from Odense, from Denmark, because the structures are quite simple. So you can even make a replication by two-step molding, and you already have a very primitive biomimic surface just for research first. But of course we do it for the large scale production. One has to do different kind of technologies, of course. But the interesting thing about this anisotropic friction is that usually if you speak to engineers and say, what do you think if my structure looking all in this direction, in which direction friction is higher? And this is a very simple question, but the right answer is actually it depends very much on material properties of the structures. So friction can be higher in this direction if you have something very made of very compliant material like rubber. But if material become more stiffer, then anisotropy will higher, or friction will be higher in this direction. So it depends on material properties and depends on the orientation of structure and on the roughness. So it is much more complex as we thought in the beginning.
Of course. Yeah. No,
I'm going to also jump in. It just came across my mind that you have a large facility for 3D printing at the University of Leeds. And then I've been wondering how far do you see us printing this kind of materials? Because I suppose bioinspired materials that could be printed would be excellent for robotic applications.
I think the challenge there is that 3D printing is normally limited in what materials you can use. So of course it's nice that you can get the shape that you want down to quite fine resolution, maybe not fine enough for, certainly not for the adhesion work, maybe for the friction. But you're generally quite limited to typically fairly rigid plastics. Or in some more advanced systems, metal and stuff as well. But I think the soft compliant materials that we see in biology and that can be so useful are hard to replicate with 3D printing at the moment. But of course, it's still a rapidly evolving field.
I would also add to that very shortly. I absolutely agree. So you can, as long as you are at the properties related to the shape, to the macroscopical shape, I think 3D printing is an excellent method. But as soon as you go into the what we call surface, then it's become quite challenging. But as you mentioned, it's developing rapidly.
Yeah. And of course, there is also the approach that people sometimes use for small scale manufacturing, where you 3D print a mold and then cast some other material in that, which
right.
Still in the topic, someone asked Professor Boyle, how do you intend to keep the robots inside the pipes without going with the flow? And I think that Professor Gorb's talk could possibly help. So I would like you both to answer how it could be responded in an industrial level.
So this is in relation to some work I included in my talk. I'm not sure if Stanislav saw it, but we're trying to develop robots for inspecting utility pipes, so clean water and sewer pipes. It's still quite early stages of the project, and honestly, I don't know how we're going to keep the robots trapped in the pipe, especially clean water. We're at the moment, we've got one PhD student within that project is looking at using hydrodynamic forces from the flow of water in the pipe to generate downforce to press a robot against the wall of a pipe so that it can, move along the pipe wall. Indeed, I was going to try and find time to ask about the possibility of materials that could adhere to a very dirty surface covered in biofilm or, half-dry sewerage or something like that. I mean, I imagine it's going to be very difficult because if you stick to the biofilm, you just pull the biofilm off. But yeah, I'd be interested in patterned surfaces that helped getting good friction or even adhesion on surfaces contaminated with sludge.
I think there are some animals which do that pretty well. Of course, this will be I would say special kind of development, and I would say it will depend very much on the size and weight of the robot. Which forces do we speak about? For example, if we speak about animals like mayflies larvae, they live on the very slippery stones underwater, and they use two different systems in combination. They use their claws on one side, and then they use also a kind of microstructure on their gills. They have external gills, and these gills are structured together with a very specific position of the legs of the femora, that they generate kind of anti-lift. That's what you mentioned before. It's like in the Formula One.
Exactly.
If you make a proper shape, the hydrodynamic forces will actually press you on the surface, and that's what mayflies perfectly do in combination with specific structures. So I think it is possible, but I think it is possible for some range of forces and dimensions.
Indeed, one of the big challenges, I think, for those of us who do bio-inspired robotics is how much bigger and heavier and clunkier everything that we make is compared to real animals.
Yes, exactly. We have to consider scaling all the time. That's right.
Yeah.
A gente tinha uma pergunta também do Afonso Telli.
Afonso Telli has a question about neural network. The question is, neural model does not respond the same way as the communities. Can we have these solutions unlikely? How far can we believe that these neural networks can be reliable in the biological point of view? That's the question.
Okay, so I think I understood most of that. through the translation. So it is very true that neural networks, which are very popular today, are loosely inspired by biological neural networks, but they are simplified so much. I mean, I think artificial neural networks have proven their usefulness in their own right, but the complexity of processing that they can do is nothing compared to, you know, a human brain or, you know, biological nervous systems. And I think one of the key problems there is that we as a scientific community still don't anywhere near fully understand how real biological nervous systems do their processing, all the different ways that information is encoded and represented. There are some people who, you know, focus on developing highly accurate models of like a single neuron. And, you know, that's the sort of thing that requires a supercomputer to run a simulation of one neuron. So I think this is somewhere where we need to be biologically inspired rather than biomimetic, because we have no real hope of fully copying everything. We just have to, you know, take some useful bits and try to take advantage. What do you think, Gabriela?
I would also add that we also have to think of the definition of the problem, and because we know that this kind of neural networks could end up with biased results. Some recent cases attest that. So the definition of the problem and the heuristics are quite important when you're using any sort of algorithm to either optimize or to try and find answers for problems. Professor Gorb, I've got a question here. So thank you for the depth in which you research the problem of adherence. As an educator, I would like to know what are the possibilities of biomimicry as a discipline in undergraduate courses for engineers who design devices and products.
Well, it's a really good question. You know, I'm a biologist by training, but I spent something like 7-8 years with engineers. Of course, I can also understand a little bit how do engineers think, and how to extract interesting features from biology to bring the biological complexity to some point understandable for engineering. But in my courses, initially, when I started at the University of Kiel, it was like 12 years ago, I started with several courses on different aspects of biomimetics. So I give for bachelor students a very general course about all the broad spectrum of biomimetics. And then in the master track, I give more specialized courses like on surfaces, like natural phenomena for biomimetics, but based just on surfaces, where we go more deeply into detail and where we do also a lot of experiments with animals, but with materials. So we try to get this link, you know, of working also experimentally in the course with biology and with corresponding existing biomimics. Or I ask my students to write the patent, for example, because it's interesting. If you have interesting results from biology, how to turn these to the patent. Because in these kind of things, we have a lot of interesting idea from students. They will be also much more motivated. Just as a tip. But 3 years ago, we opened these courses for the engineering faculty. So this is for them kind of export from biology. And we have something like 20% students from engineering department in our biological courses devoted to biomimetics. And I must admit it works perfectly, because every student wants to profile itself. Biologists try to show how good they are in understanding natural phenomena, and engineers try to show they understand equations and so on and so on. So, and especially I think it has another interesting aspect to merge more female-based research and male-based research. So Because in biology we are dominated by females, and in engineering by males. So I think if people meet in the middle, it's also not that bad.
Totally. If you don't mind me just chiming in with a thought on that, I think to some extent it's maybe something that you can't really teach, you know, how to be good at bio-inspired stuff. And I'm not saying that I am good at bio-inspired stuff, but I think the essential thing is having a good understanding of at least the relevant part of both of the fields. So in my case, I trained as an engineer and then came to sort of bio-inspired biomimetic work in my PhD. And I spent a long time reading a lot of papers trying to come up to speed with, you know, the sort of molecular biology or the genetics and stuff like that. I'm not sure you can fit enough of both in an undergrad, but I think giving people from one side or the other a taste of the other side is great, and that will hopefully capture their interests, and then in their postgraduate research they can, you know, go on and dive deeper.
Taste, it's the right word, and maybe respect, because you know, usually biologists think that, oh, engineers, they simplify everything, they try to model everything with the sphere, and then the same thing is from the engineers. They say, oh, biologists, they are too complex and too messy and don't know math and so on. But the truth is that we need more respect to the engineering, because you know, the very interesting argument of biologists is they always not satisfied with what engineers done, and say biology does it better. But biologists should not forget that this was done not by them, but by nature. And engineers, they have done it by themselves. So we need actually more respect to each other, because both disciplines are very complex and we need each other.
I agree completely. Yeah. And I think as someone who trained as an engineer and then spent several years trying to, you know, properly understand biological, in my case, neural control of locomotion, it's just too damn complex. You know, even the simplest organisms that we study, when you zoom in with your microscope, you know, mentally, metaphorically, at every level of organization, there's just more and more and more complexity, all of which is relevant, you know, to the functioning of that animal. It made me realize just how rudimentary the robots that we as humans design are compared to, you know, an ant or a bacteria or a worm.
When I go to the scanning microscope, I usually tell my people I fly to the planet Fly, or to planet Beetle, or to planet something.
Yeah, it's like a solar system inside
one planet.
Yeah.
Still on the same topic, another question, and I think it applies for both. Thank you for the lecture, very rich in content, and that allows many reflections on the biology/engineering relationship, especially on product design and biology. I noticed that the material designs are far from what the insects did. Does the design of frustration hinder the work of the scientist who works with biomimetics? It's originally for Professor Gorb, but
okay, sure. Well, I would not say that I don't see actually not that much frustration, because I think we have to see it as a challenge. We have to see it as an opportunity. Well, maybe not frustration. Maybe I'm not the person who can be frustrated. It is, of course, not exactly what insect did. And actually biomimetics, like Professor Boyle already mentioned, actually biomimicry or biomimetics is maybe not exact word. Maybe inspiration is the right word. Of course, we have to get rid of complexity somehow. Of course, we have to concentrate on essential feature for particular problem. Of course, we cannot make a exact copy one-to-one, which is impossible, but we just don't have to, because maybe we can reach the same effect in the particular design application by much more simpler means if we understood the principle. So that's why we usually speak, when in our work we speak about understanding principles, and as soon as we understood them, we try to get something, well, working similar as much as possible. But of course, we are frustrated by the market, because of course the market, it is like also kind of natural selection. Unfortunately, I don't have the slide now, but in my lectures on biomimetics, I have a really nice slide showing 3 different estimations from 3 different companies. How many ideas do we need to get to the project within the company? And then how many, from how many projects we get, how many prototypes, and then how many products, and then how many of these products will be successful. And it is, if you, different companies give different numbers. The optimistic guys, they say 0.1% from the original number of ideas to the product. But people who are frustrated, they say 0.03% from the idea to the product. Well, it is number which might frustrate people, but I would say if we don't feel the original pool of ideas from above, at some point we will not get anything at the end. So we need more idea. So, and this is a big problem actually from the grant givers, from the supporting body, from the financial part of the biomimetics, that they always expect that after every single project we will get a product, but this is not possible. And this is where frustration coming from. And of course, it is also our problem, because maybe we promised too much. We have to say we must work on biomimetics, but not to promise too much. That's my point.
I think the problem is that if you don't have big promises in your grant application, then
yes, that's it.
If you don't mind me just picking up on a few things that were said there. So I think one sort of side point is that I think it's important to think of the distinction between biomimetic and bio-inspired work. And I mean, I would define the distinction as one is trying to copy the biological system in as much detail as we can, while the other is trying to find those core principles, abstract them, and use them for useful stuff. And I think probably biomimetic work is most often useful for knowledge itself. You know, there are certainly some cases in my field, people who work on insect-inspired robots and try to use those to better understand the insects rather than to make useful robots. But yeah, if you are trying to do application-focused work, then I think at best bio-inspired is what you would want. And I have to admit, you know, I think my core interest is bio-inspired robotics, but I do a lot of non-bio-inspired robotics because often the correct solution involves wheels instead of legs, or, you know. But yeah, I think you're right about needing to manage the expectations, and the fact that understanding the biological system well enough to extract those core principles could be 5 back-to-back academic careers on one organism. You know, we don't have that long, but
but you know, another aspect which I think it's quite important too. I mean, we are pushed today, no matter in which country, it is UK or Germany or Brazil, we are pushed to do something useful, we're pushed to do something applied, and so on and so on. But we don't have to forget that actually the human knowledge works a little bit different. I think we are most productive in things which drives us, which we love to do, and I think we don't have to forget that, because I participated in many different big projects where a lot of people were sort of, well, you have to adapt yourself somehow. Actually, I don't like it, but I have to do that. And accordingly, people are not very much motivated. And I think it is very often better to have already results before some need from the engineering or whatever will come. I think Corona is a very good example that we were absolutely unprepared for that, because we were concentrated on something different all the time, because we thought that something else is much more important than that. And if biologists would, in spite of doing biomimetics, maybe go in the rainforest and look on the pattern of the viruses of every single creature, maybe we will be much farther in these area. And now definitely we will start thinking about that, and definitely we will have a lot of applied research going in this direction, which is maybe a little bit too late. So that's why I don't like these politics, but we are forced to do that, and we certainly doing that. And maybe very last point from me in this direction is that we, as biomimeticists, we always see biology as an area to exploit. But the question is, what can we give back to biology from biomimetics? And that's why I very appreciate that you mentioned, okay, by doing biomimetics, you can better understand biology. That's what we give back to biology, which is as important aspect as give something for engineering, for me personally.
Yeah. No, I agree completely. And maybe even we could give back more to biology in the sense of finding solutions which allow us to have a less of a negative impact on the planet. You know,
yes, absolutely.
The thing you mentioned in passing of plants with surfaces that make them insect proof, you know, that would mean you don't need the pesticides. You suddenly move to a much more ecologically friendly way of farming. You know, if that was...
I agree.
And perhaps in a very optimistic way, once we get more bio-inspired or biomimetic designs out, and people would start to have some sort of awareness of how important nature could be for technology. That's very optimistic again, but perhaps that could also foster some sort of interest for sustainability and other awareness against climate change. Or
I'm too much of a cynic about what humans are actually like to bet on that, but you never know.
Yeah, there was the disclaimer about the optimism before, yeah, but I think I agree with you. So there's another question.
I used to give a lot of public lectures to different age groups, and especially if you speak to young kids. And if you emphasize that, of course, the talk would be not complex as today, it will be much easier. But if you emphasize at the end that, guys, I hope after this talk you will have a much higher respect to the ordinary fly, I think kids appreciate it very much, and they see the world with another eyes. And it is much better as to tell them hours long about how it's important to save nature and save the rainforest and so on and so on, because they got that they got an impression that every creature is unique and complex, and they appreciate, you know.
Yeah, totally. There was actually one other thing in what you said a little while back there that I'd like to just revisit, which was around the constant pressure to have, results. Well, no, maybe not results, but potential commercial results, right? Which I think in engineering, as opposed to science, perhaps is much more dominant. I think that introduces some real problems, which we as a research community should try to find a solution to, because any solution that you can kind of clearly see the pathway for is inevitably going to be quite high TRL technology readiness level, quite mature technology ready to be applied to products. And sure, that can make interesting products, but all the really revolutionary world-changing solutions that are out there still to be discovered, you can't see the pathway yet. You can't promise to deliver a prototype in 3 years. And so I think it's really important that within engineering, in a similar way that I think still exists within science, that people be given the time and freedom to explore crazy ideas, new ideas, new directions, where there is maybe only a 1% chance that anything valuable will come out of it. But if we don't try for those really new things, then you know, there's never going to be the next transistor or the next, I don't know, genome sequencing machine or any of these really big important developments.
Yeah, I suppose even in publications, we kind of had a similar experience, because when it comes to something that has a prototype, that has an embodiment, it gets much easier to explain your idea, whereas when you're working at a more abstract level, you get into some sort of trouble publishing or trying to explain something that would be,
I mean, yeah, in our case, this was specifically because we were trying to present purely simulation results that they weren't really science studying an animal, they weren't really robotics building robots, they were somewhere in between, and I think very interesting work. But I think the flip side is that while it might be easy to churn out papers about some robot prototype you built, those papers normally have 0 citations 10 years later and make no impact. The papers that, you know, end up with hundreds or thousands of citations are the ones that have generated some new knowledge that people can build on. And it sometimes makes me wish I was still a scientist rather than an engineer, because, yeah, so much application related work within engineering doesn't really sort of generate follow-on work the way that good science does.
I would also say my experience with the engineering publication is that engineering science actually started to take publication seriously in the last, I don't know, correct me if I'm wrong, maybe 10 years, because lot of journal appeared, because previously I think in engineering community was, especially in robotics, was important to show a prototype or to show the robot with a short video or explanation, and that's it. So now especially in the robotic, I really see a lot of journals appeared which really consider science, and they look at the statistics and many different things, while before it was not the case. The robot is running and that's good.
Yeah, I made the thing, here's the thing.
I made the thing, look.
One of the problems that I encounter is that the sorts of people who typically become robotics PhD students and postdocs aren't the sorts of people who enjoy writing papers. They like building prototypes. So man, it can be so hard to get your damn PhD students to write the papers and stop, you know, playing with the prototype in the lab. But I suppose that's something I need to learn to manage or something. But yeah, no, it's very important publication.
I know that from the colleagues. So well, in biology, we still have the old tradition of publishing and publish also negative results and so on. It is still not the case, but I think it's also as important as positive results, because from this point of view, there is no negative and positive results. There are just results. So that's why.
I agree completely. My first paper during my PhD was a conference paper that was basically a negative result, and actually been cited quite a few times. So yeah, no, there's value in them.
Sorry if I
waste your time doing this again. I've tried it. It doesn't work. Let's move on.
Quite valuable, actually. I think we should publish more negative results. Sorry, I'm rushing through some questions for Professor Jordan Boyle. He can only stay with us until midday Brazilian time. There are a few more very interesting questions from Patricia Howard. So thanks very much. Thank you very much again, Patricia. So there are 2 questions here. I'm not sure if you can read them. They're quite long about the swarms. That could be, one of them is about human pipepods that would be what UK healthcare system is doing at the moment, and another one about human swarms for environmental monitoring, which I quite enjoyed. Would you like to comment on them?
Yeah, certainly. So I'll start with the human pipebots one. Yeah, so in fact, I briefly worked in medical robotics, looking at robots for colonoscopy. And indeed, from human pipes to utility pipes, there's some logic there. So the capsule, the pill camera capsule that you talk about, I think has been commercially available for a while now. Maybe just starting to be actually used here in the UK. The problem with them is that they essentially, you just swallow it and it goes with your digestive flow and snaps pictures every however often. And they often get bad pictures, not capturing the thing that you need to see. So they're really only used for the small intestine that we have no other way to get cameras into. I think for the notion of like swarm robots in the human body is a very appealing one. And I've certainly seen some papers that claim to be going in that direction. I think the issue comes back to that thing I mentioned earlier of how compared to biology, our tools are so limited. So making robots that are small enough to be deployed in a human body, moving around, imaging, is I think decades, at least decades away in terms of the technological capability. There's some interesting sort of isolated ones. Saw a piece of work with these little helical robots actuated by an external magnetic field that was supposed to, I think, go in someone's eye or something like that, to tackle.
I think teeth and catheter tubes, if I'm not mistaken, to remove biofilm.
But yeah, so I think the real problem there is that we are struggling to miniaturize robots as much as we would like to. There's some very interesting work on that, sort of quite not very mature yet, around sort of alternative approaches for making very small robots. With humans, with that sort of human diagnostics, I actually think the future is probably going to be improvements in imaging. With CT and MRI, you can already see so much. So I think maybe where little robots might have a role is in like targeted drug delivery or something that actually requires intervention. And then for your other question, Patricia, about a human swarm for environmental monitoring, yeah, it's a very interesting way of looking at it, viewing a team of humans sort of distributed as a swarm. I think it's a very interesting point from a philosophical point of view, maybe not directly applicable because, I mean, of course, human labor can be cheap, but individual human lives are, we like to think, highly valued. And also we're quite big and bulky and, we can't go underwater for all that long and all these sorts of things. But I think where that sort of mindset is seeing some application is in sort of data processing. So like, I think Amazon has that mechanical Turk, or what's it called? But I think they offer some platform where you can farm out, for example, classification of images into different criteria to just a bunch of people who are working, for a bit of money, clicking on where is the duck in this photograph type stuff. But yeah, I suppose where humans don't satisfy the swarm thing definition is in the fact that we are very, well, we like to think we're very intelligent and very sort of complex. So we can do quite a lot individually. Yeah.
I suppose that for the robots to act inside a human body, we need some further work from Professor Gorb, especially studying insect size and stuff. So yeah, that's maybe another.
Maybe 10 years ago, some colleagues at my university did some work on a robot that was almost certainly inspired by your work on adhesives, where they were trying to make a gecko-like robot to walk on the inside of the abdominal cavity during keyhole surgery. It didn't work, is the short answer.
But you're right. It's still too complex for medical application. It's still a long way.
But perhaps for things like simpler medical cases, like surfaces on grippers for use.
I agree, absolutely. Actually, as biologists, we have to always ask the question, well, is the gecko kind of adhesion applicable to these kind of slippery surfaces? We discussed it a couple of minutes ago about, the biofilm and so on, but also inside the body, peritoneum and all these kind of tissues are very slippery, and definitely directly with this gecko stuff will be different. So that's why some years ago, and also this is the answer to the previous question about future directions, we started looking at parasites, because the animals who mastered adhesion and leaving and locomotion inside the body or inside the tissue are the parasites. And there are four main principles, and not more than that, sometimes in combination, on attachment of parasites. And no one these principles related to the gecko-like stuff. So they do it just differently according to different principles. So also from biology point of view, we speak about biomimetics. There are two approaches, this bottom-up approach and top-down. So if it's engineering driven or market driven, then we have to go back to biology and look what prototype or what blueprint should we take.
Professor Gorb, eu acho isso muito interessante, inclusive estavam conversando.
Professor Gorb, this is very interesting. We were talking about idea generation for the biologists. All the knowledge is built, but some ideas come up and they shorten up this path of knowledge. It's something that we believe will take a long time. Maybe there is someone coming up with a new idea that shorten up this path, then in 20 years, instead of 20 years, 15 years, shortening this path. This idea is interesting, and this happens. And Dr. Boyle, I'd like to ask you one more question, if we may. We do not want to delay you. It's a question from Mariana Hayes, and she says that the presentation was excellent, and if you intend to test algorithms, Simon's algorithms, like longevity or stress level.
So the one bit I didn't catch there was right at the end. So test Simon's
PhD algorithms in Simon's PhD, like longevity and stress levels.
Okay, so in terms of the longevity, I assume you mean sort of in terms of how long these systems could last, continue to operate. That's something that I'm very interested in. For quite a while, I've been wanting to sort of explore robots that can be self-sufficient, can, operate for a year in an environment doing some task. And Gabriela's work was also sort of going in that direction. I think the biggest challenge there is how to physically have those robots gather the energy that they need to keep going and to not break as well, I suppose. So I suppose the short answer is it's something I'm interested in, but not something I have concrete plans for. Also within my pipe robots work, we want those robots to just stay in the sewer for, months at a time. Realistically, I think that's probably going to have to involve putting in recharging stations for them and having them go back to them. And even then, it's super hard, and I'm not promising we're actually going to do it. But yes, I think the idea of robots being able to actually fuel themselves from something they can get in the environment is very attractive. Also slightly worrying from an ethics, risk point of view. At the moment, a robot needs me to charge it up, so it can't run amok for long. If we were, releasing environmental monitoring robots into a dam and, giving them the ability to charge themselves and operate for years, then we very much need to think about what happens when it's time for them to die. And then before me, there were some questions in there for Prof. Gorb. Did you catch your ones? Stanislav, did you have the translation on?
Yes, I catch one, but I already, by listening to you, I've forgotten. Can you repeat it shortly? Sorry.
Gabriela,
I think shortening time. Sorry, thank you. Now I remember. It was the question about how to shorten the time. Well, this is a good question. I would think that in order to shorten this time, we need indeed more collaboration between biologists and engineers, a real collaboration. This is one way to shorten time, because usually biologists produce a lot of stuff which is published, and then until it is start to be used by engineers, a lot of time is passing through. So I think by combining different people from different expertise to the team, maybe this will shorten time. Another thing is that we are all scientists, or scientists and engineers, but we are still not the commercial, not the people from the companies. If you start to speak to people from the company, you realize that most of the companies, or many companies, they are not really interested very much in your results. What they're interested in, if you have already the product, they are happy to make it, to find a market for that. They are happy to design it, but you should prepare your ideas not to the level of the prototypes. In the best case, it should be already more or less ready product. Exactly. So,
and you've got to have that patent or design rights or something to protect the IP as well. Otherwise, they won't be interested in.
Well, yes, exactly. And of course, they will be interested if the patent really is strong. But very often the way they look at your patent and say, okay, the patent is nice as an idea, but it is very general patent, and we will adapt it to our kind of technology. And that in a very short time, your patent will be broken, and you have nothing out of that. Especially the big companies. You know, the companies, I don't want to call some very big companies, they were initially very, very innovative and made a lot of interesting kind of technologies. But meanwhile, one company I used to work with, they have more lawyers as in comparison to the developers. So they just take half-ready ideas and make the patent out of that, and claim that, well, they drive technology. So it is very long and I think very painful discussion how to collaborate with a company. And I think everybody who did that can show good examples and bad examples. And I think this communication between academia and industry, if we do it maybe in some proper way, maybe this is where we can shorten the time.
Yeah, that seems sensible. Just as a side point, I hate the way the patent system works. It feels completely dysfunctional to me. I mean, I get the principle of it, but
so, some of the companies, also quite famous company, I can even, in this case, I can call the company because it's positive, 3M. They say, meanwhile, they do less and less patents because the idea is to quickly make money out of the good idea. If idea is really good, then within a couple of years before the patent will go through, and you know, they make
it's already
money
on the shelves.
And exactly, and then the other colleagues can break the patent, and then, you know, because the strategies in different countries to the patent, as we know, is very different. So that's why not to show the good guidance to the people, better not to write a patent. This is a big question, to patent or not to patent.
Yeah, yeah, especially as academics, because I don't know about your university, but like, the whole patent process is so expensive that it's almost impossible to get the university to cover it.
Exactly.
And even once you have a patent, it's only worth as much as the legal team that you have to defend it.
Exactly, and it costs tremendous amount of time, because in the end, if you have, even if you have a supporters at the university and they really do the good job, but they have so many other patents, and of course they cannot be so deep in your technology. So in the end, the work should be done by yourself. So to produce too many patents is also not good. But this is also kind of natural selection, that only really good ideas maybe have to be patented.
Survival of the fittest, indeed.
Yes.
And with that, I must apologize and say thank you so much for inviting me. I have some second-year students I have to go and teach, so I'm afraid that was not something I could reschedule. But thank you so much. It's been a pleasure. And Stanislav, really nice to meet you. And if you don't mind, I'll drop you an email because I'd like to talk a bit further about sticking to pipes and stuff like that.
Jordan, it was also a pleasure for me to meet you in person. And well, I'm glad to continue that discussion. Bye-bye.
Yeah.
Thank you very much, Jordan.
Bye.
Obrigada, professor Jordan. Foi prazer ter você aqui.
Professor Gorb, thanks for staying a little longer.
But I see that the number of participants is dropping as water.
Yeah, unfortunately, Professor Jordan couldn't reschedule. So I would like to ask you, because in my presentation, I'm not sure if I sent you in advance, I'm sorry about that, but I've been looking at some projects in which they are enhancing what's the name? Sorry about that. Jellyfish, for example, with robotics extensions. And in one of the examples that I've been, one of the projects I've been working on at the moment, we've been trying to use, well, we've been thinking about using mussels or other clams or whatever to monitor water quality. What are your thoughts about this kind of project that mixes a little, that uses organisms, living animals for designs? What are your thoughts about that?
As a kind of biosensor, this is the question. Do you speak about using animals as a biosensors, or you speak about, well, designing sensor based on some sensory system of the animal? Because this is two different track of research, right?
Using animals as biosensors.
As biosensor. Well, I am not in this field exactly, but well, what is known to me, not far away from Kiel, in the next little town, we have a company. They even make some kind of devices for this purpose. In fact, this is basically the water tanks with a lot of video cameras which just track the trajectory of for example, fish, or for example, Daphnias, and depending on the chemicals, but of course it should be kind of calibrated for different chemicals. They look how, depending on the water quality, they change their behavior, and they you know, I think this kind of research was started many years ago by looking at the spider webs under drugs. If the spiders are under drugs, they change the shape of the spider web, and apparently you can define the kind of drugs. But you know, the gas chromatography becomes so powerful that it makes no sense anymore. But if you speak about mussels, I know that also in Germany there were some trials to make even a kind of biosensor based on the mussels. Maybe, I don't know, maybe you read the literature. When the mussel shell got some well, piece of metal, and the substrate they used, there was also metallic substrate, and then they just measured how wide is the opening of the shell. And they work not on one single animal, but on an array of hundreds of animals. And then you can get like a collective response of the organism to the water quality. That's all of what I know. I don't know how promising is that, because we don't see this kind of biosensor very often. It means to me that it's probably there are some challenges to overcome. There is some promising, but there are some challenges. I also heard about some electric fish. They, for example, changed the frequency of their electrical charges from 400 hertz, which is stable in normal conditions, but they change the frequency depending on the water quality. And apparently people use it to monitor water quality in some small towns. But I don't know the current research. I know that this was done, but I'm not the right guy, let's put it that way.
Ok, a gente tem uma pergunta para a doutora Gabriela agora.
Dr. Gabriela, we have a question from you. Ana Cláudia Garcia. Why do you choose the golden mussel to measure the quality? Because of their filtration characteristic, or is there any other reason?
So we have some in our lab, so it's going to be easier to test, and we somehow, after a few years, more than 10 years, studying the golden mussel, we kind of know how it behaves when the water quality changes. So that's the first thing. We know this organism, we have it in our lab, we have the permit to have it in our lab, but I'm pretty sure that we could also use some other organisms, especially some bigger ones that would make the design less challenging, but also maybe even some other invasive species. So we have Corbicola here. It's also an invasive species, and we kind of have to deal with it. And it's already invaded many environments. So one of the reasons was, yes, that it's easy, we have it in the lab, but also it has one of the highest filtration rates among other mussels, and especially a very good sampler of the water, if that makes sense. So you can sample a lot of water. So we have to further investigate, as I mentioned, but I think we have something here to start working with. Thank you very much for your question. Professor?
May I ask you a question, or a short extension to this question? But what if the water quality is so perfect as, say, distilled water? This is the purest water quality we can imagine, but maybe for the mussel, it is not that good. How do they react on too clear or too good quality of water?
I'm pretty sure my colleagues, there are biologists and ecologists would answer this question better. But I suppose that once the mussel is there in the water, it has to feed. So it has to open the valves and use the gills to filter the water. If it's too good, I suppose distilled water would probably kill the golden mussel. It would probably lose salt and stuff. So and that wouldn't be appropriate for drinking. So I suppose that we will have to find the right applications for that. But in our lab, we observe that when the conditions are not ideal, they close their valves. So for example, when we have too much ammonia in the water, or we don't have enough oxygen, they kind of resist to go outside. So I suppose it's a pretty good measurement. Of course, it will have to be complemented with other sensors or the types of measurements. But what we noticed in previous experiments is that it can be quite sensitive to certain substances that are toxic. Including some substances that were proposed to fight the invasions, to fight the biofouling. So nowadays we have many solutions that work pretty well, and I think that answers some other questions that are here in the Q&A. We have many other solutions, they're industrial solutions, and they mostly deal with the whole organism, and so it doesn't need to penetrate the organism. It acts in the shells and whatever, and it kind of destroys the organism. So we have to further test that, definitely, to see to what extent we can use that. But I think so far we kind of have a positive heads up about it.
I see. Thank you so much. If you wish, I can share very shortly the screen. Maybe it is really interesting for you very shortly to show you.
Oh yes, please.
These couple of things. Can you see it?
Yes, yes.
I don't know,
Oh, great.
maybe it is known to you, maybe not. This is this kind of Daphnia toximeter, which are based on tracking of the Daphnia motion. And this is a kind of muscle toximeter, which is, I think, pretty old stuff, where people just put an array and measure the opening angle. And this is the electric fish monitoring drinking water. Changing frequency, what I mentioned. And one can use, for example, the beetle antenna, or insect antenna based biosensor for monitoring whatever, very special kind of chemicals, just as an idea. Thank you.
Thank you, Professor Gorb. There is another question. It's been verified that animals with a lower safety factor, they get advantages in other abilities like speed and movement speed related to others with a lower safety factor. I'm not sure if I translated it very well.
It's proper translation. It's very good question. The honest answer, I don't know. The animals with low safety factor, I'm not sure if they have a lot higher, or if they can have higher speed. They just cannot adhere that well. But animals which can adhere well, they have a quite different. They have a different. It's a good question. I cannot bring it into right relationship. Animals which cannot adhere well, they are not necessarily much faster. That's my point. Animals which adhere very well, of course, if they use adhesion for walking on the ceiling, they walk not that fast, because walking on the ceiling is always challenging. But if they walk normally, not on the ceiling, they can walk, of course, much faster, because they don't engage the adhesive organs into contact with the surface. They usually try to keep the adhesive organs far from the surface. And for example, I will give you a very good example, which we can discuss from the point of view of reflexes and preflexes. You know what reflex is? The most of biologists know what's that. That's if you get a signal and then you get this signal through the sensory organs to the nervous system, and then you will get back answer to the muscle. That's what we call reflex. It is pretty quick reaction, but it takes still some time. But in some biological structures, they are designed in the way that they don't have to have any reflex. So the properly designed mechanical structure will react immediately according to the situation. A good example is the adhesive organ of the bee, of the honeybee. They have a close, and then above the close, they have adhesive organ here. And if they walk on the rough substrate, if the friction between the close and the substrate is sufficient, then adhesive organ will never be engaged into the contact. But as soon as the close are slipping on the surface, the adhesive organ will automatically come into the contact and generate adhesion. So from this point of view, they can walk quickly on the normal substrate, but as soon as they need more adhesion, they automatically do that without using the nervous system. And this is the fastest way to react to the environment.
Still on a similar topic, Eric was wondering if there is any kind of mucus production in the gecko feet.
No.
And if all the animals that you mentioned have some sort of solution to help them attach to surfaces, or is there any kind of polymerization in that process?
Okay, all the animals I discussed in this talk well, it's not true to say they don't have anything in contact. This would be probably not true. Well, there are two groups. The first group, they produce some substances in the contact, and most of the insects, they produce some lipids. Geckos and spiders, they don't produce anything. They have absolutely dry contacts. And the main difference in the structure between these two is in the size of the hairs. If the hairs become very, very, very small, then you don't need any fluid, because the hairs, they are so, I would say, floppy, that they can adapt to any kind of surface profile, including even the molecular roughness. They can still generate good adhesive contact without having any fluid. But as soon as the adhesive organs become larger, then you need some fluid. But this is not the mucus. The mucus is known only for the tree frogs. They produce mucus.
Thank you very much. I'm trying to look for more questions.
Gabi, acho que tínhamos uma pergunta no chat. Acho que você consegue ler.
Encontrei. Just a second. So, a question from Emma. I was wondering if there are any ethical implications involved in using living organisms as biological sensors, if these would present unique challenges.
Well, it depends from point of ethical issues. I would say if you follow the prescription of the ethical commission, I don't know about the Brazilian, but I think it's worldwide pretty similar. I think for the invertebrates, with a couple of exceptions like cephalopods and decapod crustaceans, we don't need any special permission to do any kind of research and even to do any kind of implication for the industry. But of course, as soon as you start to use vertebrates like mice and geckos and so on, in this case, you have to get some permissions depending on your kind of experiment or kind of application. Of course, at some point, if you use any vertebrate animals, you will face to some ethical issues. But if you work with insects, so far insects are not really protected by any ethical things.
There's a question here. There's someone asking if your laboratory offers scholarships for masters, PhDs, and other Latin students. So I suppose someone wants to work with you, Professor.
Well, I must admit we have actually quite good collaboration in Brazil. I collaborate with another entomologist, and it's again another topic. We work together on the colors because many years ago I did my master thesis on dragonflies, and we study the coloration and the physical colors of dragonflies. And of course, the tropical dragonflies are offer much more nice coloration patterns, which are not studied at all. And I think in Brazil there are a lot of even undescribed species of dragonflies. So we work with Professor Guillermo Ferreira from Sao Paulo, but I think he is moving now to another university. So the answer is yes, sure. We accept the students over the world. We need good students, and all our equipment can be used, and I'm happy to collaborate. But of course, it is difficult to provide this amount of fellowship. So, but you know, Germany actually has many interesting fellowships for the foreigners, like DID. This is the German Exchange Office, and of course they they offer travel grants for students from Latin America, and of course you are more than welcome to apply if you are interested in these kind of topics, of course.
Professor, we have about 10 minutes left. I would like to thank you again for being with us. Is there any question or anything you'd like to say before? I think we went through all the questions. So we have some extra time just in case you want to say something that you find particularly interesting that you were not asked.
Thank you so much, because it is not only interesting topic and as far as I understand in Brazil, not very well known. So thank you for spreading this idea over the big amount of people in Brazil. Thank you for inviting me to give you some overview about our activities. And I was really pleased to know Professor Boyle. Thank you so much for organizing, and it was perfectly organized. Compliments.
Well, thank you very much. Your talk and having you here was very enlightening. Thank you very much, Professor Gorb.
Thank you, Gabriela. Thank you, Clara. Bye-bye.
Bye, professor Gorb.
Bye-bye.
Muito obrigada. Bom, então, gostaria de encerrar essa mesa redonda. Agradecer a doutora Gabriela Rabelo pela mesa.
I'd like to thank Dr. Gabriela Rabelo, the organization, for today's lecture. And we conclude the first day of CBA Fórum. I'd like to invite you all that are here and all the participants. Tomorrow, 9 a.m., we have our second day of the forum. And I believe that's it. See you tomorrow. See you tomorrow at 9 a.m. BRT. Thank you so much. Bye-bye.